Hello everyone, my name is Jushen ZHANG. I'm at Z ID is Z5422441 and this is my student card. And today we are going to dive into the fascinating world of the solar system and the mechanics through our PHET simulation experiments and demonstrating the Kepler's laws of actions. Kepler's law of planetary motion are the three rules that describe how planets orbit around the sun. And Johannes Kepler formulated these laws in the early 17th century, and let's go a bit deeper into each of these transformative laws. The first law is the law of orbits, and we also call it the law of ellipse, and state that the planet moves in an elliptical orbit with the sun at one focus of the ellipse and not in the center. And the second law is the law of areas. We also call it the law of the equal area, and it tells us that the length segment connecting a planet to the sun sweep out of the equal area during the equal interval of the time. And the third law is the law of period. And we also call it the law of the harmonious and qualifies the relationship between the optical period of the planet and its distance from the sun. And specifically, it states that the square of the planet's orbit period is proportional to the cubes of the semi-major axis of its orbit. And this law will allow to predict the orbital period of any planet once we know the distance from the sun. And it also implies the harmonious relationship among the orbits of all the planets in our solar system. This slide shows the answer to the question 9 and the planet and the moon scenario. And in our simulations, observing the Earth and the Moon system provide a clear example of how this law works. And interestingly, while the Moon orbits Earth, the Earth itself moves slightly due to the gravitational pull from the Moon, and showing that both bodies exert a force on each other. And this Moon is more evidence when we compare to the Sun and planet interactions, and where the Sun's massive size makes the movement almost imperceptible. And such the observation finds helps us to understand the dynamic and the reciprocal nature of the gravitational force in the two-body system. For the answer to the question 11, in our PHET simulation on optical mechanics, we use grid line to measure the distance, with each grid line represent one astronomical unit, and the average distance from the Earth to the Sun is about 149.6 million kilometers, and this unit can simplify the calculation in planetary orbits and provide the practical scale for simulations like ours. And by setting the grid lines to 1 AU apart, the distance from the Sun, from Earth to Sun in the model directly corresponds to the space between each grid line, and making it easier to visualize the solar system's vast scale. And using 1 AU in the simulation ties to the Kepler's law, and which links to the planet's optical period to the cubes of its average distance from the Sun. And for example, moving the planet to 2 AU or 2 grid line away and increases its orbital period in line with the Kepler's prediction. For the questions 14, our measurement of the optical period at a different distance provided empirical data to support the Kepler's third law. And for example, as we double the distance from the Sun, the optical period increases significantly, not linearly, but according to the cubic relationship described by the Kepler. And these practical observations through the simulations helps our grasp the immense impact distance has on optical mechanics and illustrating the interconnectedness of celestial bodies' motions within our solar system. For the questions 15, by applying the formula for the optical velocity, we could calculate and compare the theoretical speed of the planets. And finally, those closer to the Sun, like Mercury, has the fastest orbital velocity, but for the Neptune, it has the least optical velocity and is really far away from the Sun. This is not only support the Kepler's laws, but also ties into the Newton's law of universal gravitation, and which explain the inverse square relationship between the gravitational force and the distance from the Sun. This synthesis of Kepler's law, Newton's law, and the conservation of the angular momentum has offered more detailed and specific understanding of how velocities are balanced by the gravitational force and its orbital distance. Finally, reflecting on our simulation experiments, we have seen the first-hand and how theoretical laws hold up under the visual texting, and I have learned the optical mechanics and the mathematical relationships and the system dynamics and the observational skills and the practical applications. And this experience has underscored the predictive power of the Kepler's law and their continued relevance in the modern astronomy and the space explorations. And moreover, they highlight the utility of the simulation in educational setting and providing a dynamic way of explore and verify complex scientific concepts and through the interactive learning. And thank you for watching, and I hope the exploration in the orbital mechanics has illustrated the laws that govern our universe, and I will stay curious and keep exploring the sky. Thank you.